Okay, our next sensitivity mini topic is adding a new variable. In Geppetto's example, each of our variables was a product line of toy soldiers or toy trains. Let's say Geppetto's interested in adding a new product line, building blocks. Let's call that decision variable X3 is the number of building blocks that he makes. These building blocks require no finishing, 2 hours of carpentry, and they contribute $1 to profit, and they have unlimited demand. Should Geppetto start making building blocks? Let's start off by writing the new linear program. The old objective was to maximize our profit, which was equal to 3x1 plus 2x2. And now that we've got x3, it contributes $1 to profit per unit. And so that's plus 1x3. And then let's think about our constraints. So we have our finishing constraint, our carpentry constraint, and our demand constraint. Now, the toy blocks require no finishing, so our finishing constraint stays the same. So it's going to be 2x1 plus 1x2 plus, we can kind of think of it as a 0, x3. It takes 0 hours of finishing for x3, and that has to be less than or equal to 100. Our carpentry constraint was that X1 took 1 hour carpentry, trains took 1 hour of carpentry, and then now our new building blocks take 2 hours of carpentry. And that has to be less than or equal to 80. And then our demand constraint, we've got unlimited demand for these. And so that constraint stays as 1x1 is less than or equal to 40. And so you can kind of think of there's a 0x2 and a 0x3 showing up in that constraint row. Okay, that is our new problem. And so what happens when we add a new variable? If we think about our feasible region, we've enlarged the feasible region from 2D to 3D. Any solution that was optimal before, or the optimal solution is still feasible. Just setting the number of building blocks to 0. And so we can kind of think of our current solution is going to set, well, our current optimal solution, we make 20 soldiers, 60 trains, and 0 building blocks. We can kind of think of X3, at least initially, as a non-basic variable. So it's not in the basis. I will maybe also write out that SF equals 0, SC equals 0, and SD equals 20. And so that's going to be our current solution, sort of considering this new product is we're currently making none of them. Okay, if they're not even in the problem, then we're making 0 of them. And now we're considering what would happen if we introduce them. And so we start them off as a non-basic variable, and now we look at what would happen if we brought them in. Well, this solution is feasible, right? If we kind of think about zeros, it sort of deletes this column, and then we got back to our previous constraints, and our previous solution was feasible in that case. Okay, but adding this new variable adds a constraint to the dual problem. If we think about our variables in the primal problem correspond to constraints in the dual problem. And so let's note down our dual variables here. So maybe we'll call this YF, YC, and YD. Those are our 3 dual variables. And they correspond to each of the constraints in the primal problem. But we can think of this column for x3 as being a dual constraint. So let's write down what that new dual constraint is. We don't have to write out the full dual problem, but we just need to ask what constraint does this correspond to? And so the dual problem will be a minimization problem with greater than or equal to constraints. And so we can essentially take these coefficients in here. So 0, yf, 2, yc, and 0, yd. And this is going to be a greater than or equal to constraint, and that has to be greater than or equal to the objective value for x3. So that's greater than or equal to 1. Okay. In essence, saying the value of the resources used for these new blocks has to be at least as much as the profit that we get from it. Yes. Yeah. Okay. So let's go ahead and fill in, well, what are our y values? So looking back at our Tableau, the y values are still the y values that we had before of 1, 1, and 0. And so for our current solution, we have, so currently, so our current dual solution is yf equals 1, yc equals 1, and yd equals 0. And we can plug those in here, and that will give us 0 times 1 plus 2 times 1 plus 0 times 0. And that should be greater than or equal to 1. And so that's 2 is greater than or equal to 1. Okay, and so we're currently dual feasible, which means that we're primal optimal. Okay. Another way to think about this, so yeah, maybe I'll write that down. This constraint is dual feasible, which is equivalent to being primal optimal. If we satisfy the corresponding dual constraint, then we're still optimal in the primal problem. We can think about looking at the reduced costs. The reduced cost here is sort of y transpose A minus C, and that would give us all the reduced costs. But if we think of the reduced cost corresponding to this new product, sort of reduced cost, think about it in terms of reduced cost. That would be y transpose times I'll write that as A3, which is going to be the third column in our A matrix, which is exactly this column here of 0 to 0. And then if we minus C3, and C3 is the coefficient of x3 in the objective, and that's 1. So this ends up being, well, this quantity here, y transpose times A3, is going to be our y vector times the 0 to 0. That's exactly what we computed over here. And so that's going to be 2 minus C3 was 1. And so our reduced cost in this case is positive. Okay. And for a maximization, a positive reduced cost is means that we're optimal. Okay. It means that if we were to try to bring x3 into our basis, it would actually reduce the amount of profit. Okay, and so we wouldn't want to start making x3. So conclusion, don't make building blocks. Okay. They're not worth it. The profit is not enough to make them worthwhile to bring into the basis, and so they stay non-basic, and we'd be making 0 of them. Okay. But what you can kind of do is you can actually sort of look at the coefficients here of, let's see, this is finishing, carpentry, and demand. And so as long as we assume demand is unlimited, you could think about, well, maybe I want to redesign these blocks in a way that might change these numbers. Essentially, I've got to either change the amount of work done so that these numbers maybe become smaller, um, or I have to raise my prices and hopefully change this number for my profit. And so if I were to charge more than or charge enough so that I get more than $2 in profit, then this inequality would be violated. We would be no longer dual feasible, and then we would be no longer primal optimal, and it would mean that I'd want to start making um, some building blocks, but that's not the case. Let's consider a fourth product. Geppetto considers making wooden stacking towers that require half an hour of finishing, 1 hour of carpentry, and contribute $2 to profit. Unlimited demand. Should Geppetto start making those wooden stacking towers? So let's look at that. And so we'll just jump straight to this stage instead of having to write out the full new constraints here. But let's see, it takes half an hour of finishing, so 1/2 times y finishing plus 1 hour of carpentry, so 1 times y carpentry. Okay. Remember, the y's are the dual uh, variables or the shadow prices. And so it takes 1 hour of finishing, and you can think of the dual variables as dollars per hour. Okay, and so 1 hour finishing times 1 hour. Essentially, this left side is computing the cost of the labor and inputs to the problem. And that cost, if that cost is bigger than the profit, which in this case is $2, then it's not worth making. Okay, and our current basis remains optimal. Okay, and we shouldn't make any stacking towers. Plugging in the current values of YF, YC, and YD, we'll get 1/2 times 1 plus 1 times 1 plus 0 times 0. Should be greater than or equal to 2. And this gives us 1/2 or 3/2. And we'll notice that that's not greater than or equal to 2. Okay, and so maybe I'll put the not through all those. Okay, and so this tells us that we violate the dual constraint. Okay, and so we are not dual feasible, which implies we're not primal optimal. Okay. What should we do then? Well, it means we should start making these stacking towers as long as we can make them with a 1/2 hour finishing and 1 hour of carpentry, and they'll contribute $2 to profit. We want to bring them into our product mix. And so while we need to modify our Tableau and then do another iteration where we bring our new variable into our basis. So let's actually kind of write out what the new Tableau would be. And so let's see, our objective row would be 1 for Z. Let's see, got to move this place where I can find it. So refer back to page 1, X1, X2. We'll call this, we skipped over X3 because we got rid of it, X4, and then S, F, S, C, S, D, right-hand side. A little bit cramped because I want to have enough space here. So copying things down, this is going to be 0, 1, 0, 0, 0, 0, 1, 0. X4, I'm going to hold off on filling that in. I'll do that in just a second. And let's see. SF is, here's our 1, 1, 0, and 180. And then maybe I'll draw my lines here. Help me fill this in. This is the 1, -1, 0, -1, 2, 0, -1, 1, 1, 20, 60, 20. Okay. Now the question is, what should I fill in there? And I don't want to immediately just take the values from the problem, because those would be the values that I'd put into the original Tableau. And if I wanted to start from the beginning, I could. But the trick is I can pick up from the end and add the column in as it would be transformed. Okay. And so what I need to do is fill in this value here is going to be the reduced cost for X4, which is going to be, let's see, Y transpose A4 minus C4. Okay. Y transpose A4 is what we got from computing this side. So that's going to be 3 halves. C4 is this 2. So essentially we're moving that over the other side. And that will give me 3 halves minus 2 is going to give us -1/2. Okay. And then this here, thinking about what that is using the fundamental insight, that's going to be B inverse A4. Okay, so I take my B inverse matrix, multiply it by the A4 column, which is this 1/2, 1, 0. And so let's go ahead and write that out. My B inverse matrix, I can read off from right here of 1, -1, 0, -1, 2, 0, and -1, 1, 1. And I'll multiply it by these coefficients of that I get from essentially the usage of the different resources. And so it's going to be 1/2, 1, and 0. Essentially the coefficients in each of the 3 constraints for that new variable. And this will give us, multiplying this down here, 1 times 1/2 minus 1 is going to be -1/2. This times here, -1/2 plus 2 is going to be 3 halves. -1/2 plus 1 is going to be 1/2. And so those are the values that are going to go in here is -1/2, 3 halves, and 1/2. Okay. The thing that I should notice once I fill this in, because I said it's not primal optimal, I see that I now have a negative in my objective row, which means that I would circle this column as my entering basic variable. X4 has enough profit that it's worthwhile to bring it into the basis. Okay, and then I would do my ratio test here. I've got a negative in that pivot there, so that wouldn't matter. Here I'd get 60 divided by 3 halves is 40, and 20 divided by 1/2 is 40. And so, ooh, actually, interesting thing happens here is we've got a tie for exiting basic variable. When that happens, you can really choose either of them to be your exiting basic variable. We'll end up at what's called a degenerate solution. So I'll pause the video, fill in what the next Tableau is, rather than kind of walking you through all the steps here. Go ahead and pause the video, try it out. Try to do your pivot here. So I'm going to choose, let's see, for simplicity, I think it will be a little bit nicer algebraically to choose this row here. Though it actually shouldn't matter too much. Okay. Try to do that pivot and we'll come back in just a second. Okay, after you do your pivot, here's what you should end up with for your Tableau. Notice that X4 has entered the basis. our new solution is now that x1 is equal to 40, x2 is equal to 0. And so this is actually called a degenerate solution when one of your basic variables goes to 0, which means that it sort of corresponds to, there's multiple different bases that give you the same solution. X4 has a value of 40, so this is maybe x1, x2, x4, because remember we skipped over x3. We didn't even consider adding it to our basis because it wasn't profitable enough. And then each of our slack variables are 0 because they're all now non-basic variables. And so that's S, F, S, C, and S, D. Okay. So that's your new solution. You'll look at the objective row. All the values are greater than or equal to 0, so we're an optimal solution. Interesting, though, you'll notice that SF, the slack for finishing, has a 0 reduced cost, which means that there are more than one optimal solution. And so you could pivot to bring SF into your basis, and you would get a another solution that had an objective value of 200, same objective value, but a different solution potentially. Okay, because of the degeneracy, it might actually be the same solution. Yes, yeah. So if you pivot on SF, SF will come in, X2 will leave, and you'll get that SF is 0 as well. And so yeah. Yeah. Yeah, actually, no, maybe I take that back. You might actually get a different solution here. Okay. Yeah, so kind of wrap it up. If the dual constraint is violated, then you're not dual feasible, which means you're not primal optimal. You can use these two formulas using A4, which is your new column from your new introduced variable, to compute B inverse times A4 to get this part, Y transpose times A4 minus the objective value for the new variable. And that will give you your new value here. It should be, for a maximization problem, it should end up being negative if this dual constraint is violated. And so that's going to be a variable that you can pivot on and bring into your basis. And that'll give you a new solution. So that sort of summarizes everything you've got to do or consider if you're introducing a new variable. Some variables will satisfy the dual constraint, and so they'll be primal optimal. You don't have to do anything. Don't make any building blocks. But in this case, our conclusion is that we do want to make the stacking towers. They have enough profit relative to the resources that they use. That's it for this video.